Hello and welcome to today's lesson on the operation of a transformer, which is part of the magnetic fields topic in AQA A-Level Physics. So in today's lesson we're going to try to explain the action of transformers. So if we've been successful and learned in today's lesson, we should be able to describe what a transformer is and explain how it operates, calculate values of a transformer system, and finally explain how a transformer works, including its inefficiencies, which forms part of the A-Level AQA Physics specification on 3.7.5.6, the operation of a transformer, which is found in the magnetic fields topic. So this is the setup of the national grid in the United Kingdom. You'll have a power station which is linked to the national grid, with a step-up transformer forming the first part of the national grid, which increases the potential difference to increase the efficiency in the cables. You then got high voltage transmission lines, which then connect to the last part of the national grid, the step-down transformer, which then links to consumers, so homes, factories and shops. So a step-up transformer is the transformer found before the electricity travels through the transmission cables. Here the potential difference goes up, the current goes down, but the power of the transformer stays constant. And this is what a step-down transformer looks like, or what we sometimes call them in the real world, a substation. So this has been found after the electricity has travelled through the transmission cables, and here the potential difference goes down, so the current goes up and the power of the transformer stays constant. Now the national grid in the United Kingdom was set up in 1926, and the government decided that electricity would be supplied to homes at a potential difference of 240 volts. This was lowered in 1994 to 230 volts. Now the reason why we set up a national grid was to ensure that cities should share electricity at the same potential difference, so electricity could be produced in different power stations around the world. Around the country. Now the electrical energy is originally produced at a power station. Now the potential difference at the power station is about 25,000 volts. Now the potential difference is then increased after it leaves the power station. Now this is what a step-up transformer does in the grid system. Now the step-up transformer raises the voltage to approximately 132,000 volts, so less current is needed to transfer the same amount of power. So as a result, a lower current passes through the grid cables. Now energy losses due to the heat and effect of the current, or energy dissipated to the internal energy of the surroundings, is reduced to almost zero. But we need to lower the potential difference at the end of the grid cables before we can use the mains electricity at home. So the high potential difference, low current configuration in the transmission cables minimizes the energy transfer to the internal energy of the surroundings. So it increases the efficiency of the power transmission. So after the electrical energy reaches the homes and buildings it needs to power, then the potential difference is stepped down to 230 volts, making it safer to use in the home. So this is what a step down transformer does in the grid system. So in a power station, electricity is generated at 25,000 volts via electromagnetic induction. Then a step up transformer increases the potential difference to 132,000 volts in the electrical cables. This is because if the cable has a high current, it would lose a lot of energy to the internal energy of the surroundings due to resistance. So we have a high potential difference and thus low current. This would increase the efficiency of the electrical energy transmission. Then a step down transformer decreases the potential difference to 230 volts, so it's safe to use at home. So we use transformers in the national grid as it ensures the electricity is transferred efficiently around the country. If we did not have transformers, the high current needed to power devices will be quickly dissipated due to high resistance in the transmission cables. So resistance causes energy to be lost to the internal energy of the surroundings. So a high current would lead to a high power loss, so energy would then be dissipated quickly to the internal energy of the surroundings, so you'd have no electrical energy at the output, so the device would not work. Now we can calculate the power loss from the electrical cable to the surroundings with the equation P equals I squared R. But remember, in this particular equation, I has to be I RMS, as it's an alternating current going through the transmission cables. So this shows us that a high current will dissipate a large power from the cable, and a low current will dissipate little power from the cable. So it's the aim of the transformer to reduce the current to the lowest possible value in the electrical cable. Now interestingly, this can also be achieved by having a low value of resistance in the equation. So in what you would also do is you can make the transmission cable out of a low resistivity material. Now the power in a transformer is always considered to be constant, so transformers work on the principle that the power in the national grid is constant and use this to lower current in the cables. Now as a result, as we know, power equals potential difference times by current, and power has to be constant throughout, and it's important that that's the same throughout the entire of the national grid. But remember, we're not talking about the power loss, we're just talking about the power in the transformer. Okay, so this tells us that when you have your potential difference increasing, the current decreases, so this gives us little power loss, as I is now smaller in the equation power loss equals I squared R. But therefore, if in our step down transformer our potential difference decreases, our current would increase, so this would give a large power loss as P equals I squared R, but it does make the potential difference safe to use at home. Now the national grid therefore is a system of cables and transformers which transfer energy around the country. Now let's just remember that power stations and homes link to the national grid but are not considered part of the national grid, and the aim of the national grid is to use transformers to allow the electricity to be transferred around the country with great efficiency. And in addition, it also means that different parts of the country can share electricity with each other. Now a transformer works on the principle of using alternating potential difference in alternating current. Now remember, transformers do not work on direct current, they only work on alternating current. Now in alternating current, the electrons move backwards and forwards or oscillate in the wire. So this means the electrons stay in the same net position in the wire, and in the mains the electrons move backwards and forwards 50 times every second. So as a result, this gives us a mains frequency of 50 Hz. Now to understand how a transformer works, we must know the structure of a transformer. Now all transformers, whatever the size, have the same basic structure. So what we have is a transformer consists of a metal core in its center. Now the core must be made of a soft magnet such as iron. Now a soft magnet is a magnet which can change its magnetic field easily. So this idea is because a transformer needs to have a changing magnetic field in its core. Now a soft magnet can produce a rapidly changing magnetic flux. Now if the magnet is not soft, when its magnetic field is changed, energy will be lost due to the process of hysteresis. Now the core needs to therefore be made of a soft magnet so it can produce a rapidly changing magnetic flux linkage. Now on one side of your transformer core you have an input circuit. Now we call this the primary coil. So for the transformer to work, the input circuit must have an alternating potential difference. So the input circuit is the circuit going into the electrical transformer. So this could be the circuit coming from the power station in a step up transformer or from the transmission line in a step down transformer. So it's important to know it's linked to the input circuit of your transformer. So it's a very, very important idea that. Now on the other arm of your core you have the secondary coil. Now the secondary coil is linked to the output circuit of your transformer. Now it's important to note that the secondary coil and the primary coil are not connected electrically. They are separate circuits. So in the transformer, the secondary coil could be linked to the transmission line in the step up transformer or to the consumers in the step down transformer. But remember, it's very important to note that the primary coil and secondary coil are separate electrical circuits. Now we can also call the output circuit of a device the load circuit as well. Now it's important that we understand the idea of a primary coil, a core and a secondary coil. Now to understand how the transformer works, we're going to consider one free electron in the primary coil wire. Now in reality there's a tremendous number of free electrons in the primary coil. Now what we know is that the free electron can also be considered a mini magnet because it's moving. Now this, remember, is a fundamental rule of electromagnetism. All moving charged objects produce a magnetic field. So as our electron moves backwards and forwards in the primary coil is part of an alternating current, this therefore will make a magnetic field in our primary coil. So this makes the primary coil wire an alternating magnet. So it makes the magnetic flux of the primary coil alternate, because remember, the direction of our electrical current indicates the polarization of the magnetic field, and because our current is moving backwards and forwards, our magnetic field is changing polarization, it's changing direction. So what we know is this produces a rapidly changing magnetic flux in the primary coil. Now this is important because the iron core is also a magnet. So the iron therefore will interact with the primary coil's magnetic flux. So the alternating current in the primary coil makes an alternating magnetic field in the primary coil, and the interaction between the primary coil and the core magnetic fields makes the core magnetic field alternate. So it gives the iron core an alternating magnetic flux. So it produces a rapidly changing magnetic flux in the magnetic core. So the iron core has become an induced magnet. Now this is helped by the core of the transformer being made from a soft magnet, because remember we said a soft magnet iron core prevents energy loss due to hysteresis in the transformer process, because a hard magnetic core will dissipate energy to the surroundings when its magnetic field alternates. Now the iron core is needed to act to amplify the alternating magnetic flux linkage produced in the primary coil, because this increases the change in magnetic flux linkage experienced by the secondary coil, because it increases the magnitude of the magnetic flux linkage the secondary coil experiences. So when that direction alternates, the change produced by that will be greater. So therefore the iron core will act to boost the induced EMF in the secondary coil. Now remember, there are electrons in the secondary coil also. So the secondary coil is a conductor, and in this conductor there's a change in magnetic flux linkage as the magnetic field of the core is alternating. So whilst the conductor, the secondary coil, is not moving, the magnetic field is alternating. So this alternating magnetic field causes a change in magnetic flux linkage. So because in this conductor there is a change in magnetic flux linkage as the magnetic field of the core is alternating, this induces a potential difference in the secondary coil via induction. Because remember, the change in magnetic flux linkage induces a potential difference in the conductor. Now remember, the size of the induced potential difference is directly proportional to the rate of change in the magnetic flux linkage, and when the secondary coil is part of a complete circuit, this will induce an alternating current. Now remember, it's the change in magnetic flux linkage which induces a potential difference in the conductor, and this is why you need an alternating magnetic field in the core, as it allows the secondary coil to experience a change in magnetic flux linkage, because a direct current in a transformer would lead to no potential difference in the secondary coil, as there's no change in magnetic flux linkage. Because remember, you need a change in magnetic flux linkage to lead to an induced EMF. So this is how a transformer can transform the current between the coils without them touching or being connected electrically. So we can show how a transformer works with the following animation. The change in magnetic flux linkage in the secondary coil produces an induced EMF in the secondary coil, which can lead to an induced current in the secondary coil. So we can see in this particular animation here, you've got your alternating magnetic flux in your primary coil, which leads to your alternating magnetic flux in your core, which then will cut the secondary coil, which will then lead to an induced EMF in your secondary coil and an induced current in your secondary coil. So we can summarize how a transformer works as the following. In the primary coil, an alternating potential difference in the primary coil, due to being part of a circuit, will produce an alternating current in the primary coil, which will then interact with the magnetic field in the core to produce an alternating magnetic field in the core. Then in the secondary coil, an alternating magnetic field in the core will then lead to an alternating potential difference in the secondary coil via the induction effect, and because the secondary coil is part of a complete circuit, an alternating current is produced in the secondary coil. Now please remember, the size of the alternating potential difference induced is directly proportional to the rate of change of magnetic flux linkage. So we can summarize the entire process as the following. It is an application of the induction process that we've looked at earlier. Now a transformer has several adaptations to help carry out its function, to help carry out its job efficiently. So this is because the induction process can lead to energy being dissipated to the surroundings. So firstly, the wires are insulated to prevent a short circuit, because otherwise the electrons would travel across the iron core and stop the transformer effect. So therefore, because the primary coil and secondary coil are not electrically linked, they are separate circuits, we need to insulate the wires to prevent that short circuit, because if the circuits were combined, there would be no change in the potential difference. The second adaptation is that the iron core is laminated to prevent eddy magnetic currents in its core. Now, laminated means that the core is covered in an insulator such as plastic. I mean, anything can be laminated. So for example, paper can be laminated. Now, if you cover something in an insulator, it means a current cannot flow in this core, which prevents an eddy current. Now, an eddy current is a magnetic field produced in the opposite direction to the wanted magnetic field. You can consider it as the magnetic version of friction or resistance. Now, a large eddy current reduces the efficiency of a transformer. Now, this occurs because Lenz's law states that when the induction process occurs, a current creates a magnetic field that opposes the magnetic field that created it, and thus the eddy current reacts back on the source of the magnetic field. And we can actually use this in many particular applications, such as stopping power drills quickly. So eddy currents are always produced as the induction process produces a potential difference which opposes the change which causes it. So when the secondary coil has a current induced through it, it must be flowing in the opposite direction to the change that causes it due to Lenz's law. So this will produce an alternating magnetic field in the opposite direction to that of the core. So therefore, this will therefore interact and reduce the overall magnetic field. So this will produce an eddy current in the transformer. Now remember that eddy currents are effects in the magnetic field, not the electrical field. Now the eddy current will then dissipate energy by generating heat. Now another way we can lower the production of eddy currents in addition to lamination is to make the core out of a material with a high resistivity, because the higher the resistivity, the lower the current produced due to the induction process, so the lower this eddy current will produce, so the smaller the magnetic field in the opposite direction, so there'll be less energy dissipated due to the heat of the object. Now, ideally, another adaptation will be linked to the two coils, because all of the magnetic flux created by the primary coil will be going through the secondary coil. However, that's not always the case, especially if the two coils are far apart. So the core is designed so the coils are as close together as possible to each other. Now, this can include winding the coils on top of each other around the same part of the core rather than being in different parts of the core. Now, these adaptations mean that the transformer carries out their functions in a very efficient manner. Now, transformers are so efficient, we consider a transformer to be 100% efficient. Now, this is an assumption and it's not true in reality, but we can use this assumption to calculate the efficiency of a transformer and look to see how close it is to 100%. Now, efficiency is equal to useful power out over total power in. So in theory, it's the power of the secondary coil, the power out, divided by the power of the primary coil, the power going into the transformer. So we know that power equals VI, so it's VS times by IS over VP times by IP. So let's just summarize what we know so far. There are many practical adaptations of transformers. Now, the iron core is laminated to reduce magnetic eddy currents and made of soft iron to allow easy magnetic field reversals, prevent heat loss via hysteresis. Now, the core is made from a material of high resistivity to lower the production of eddy currents, and the wires around the transformer must be insulated. Now, we also know that transformers are very efficient, but larger ones require cooling, usually with oil, but we can calculate the efficiency of a transformer easily. We know that efficiency is equal to useful power out over total power in. So therefore, it's V out times by I out over V in times by I in, or we can consider in terms of primary and secondary, it's VS times by IS over VP times by IP. Now, transformers are used in the national grid to change the current and potential difference at different points. Now, we can observe which is the step up transformer and which is the step down transformer by looking at the amount of turns of coil in each particular arm. So the number of coils in the transformer relates to the amount of potential difference induced in the wires, because the more turns or coils of wire, the greater the induced EMF. This happens as the greater the number of coils, the greater the change in flux linkage, as you can think of it as n is greater in the equation, magnetic flux linkage is equal to BAN cos theta, or you can think of it as the following, that the thicker the conductor, the more field lines which pass through the conductor, the greater the change in flux linkage. Now we also note the following, that in a step-up transformer there are more turns in the secondary coil than the primary coil, so the potential difference goes up. Now we can visualize a step-up transformer as the number of secondary coils is greater than the number of primary coils, because remember, the more coils, the more potential difference, because the more turns or coils, or the flux linkage per second will be greater, so there's a greater change in flux linkage, so the more potential difference is induced in the coil. Now the other way to identify a step-down transformer is saying the number of primary coils is greater than the number of secondary coils, because in the step-down transformer there are more turns in the primary coil than the secondary coil as the potential difference goes down, because like we said before, the more turns or coils, the greater the flux linkage per second, the greater the change in flux linkage per second, so therefore the more potential difference induced in the coil. So we can remember by saying the following: in a step down transformer, the number of primary coils is greater than the number of secondary coils, and in a step up transformer, the number of secondary coils is greater than the number in primary coils. Now we can express this concept a little bit more mathematically, because we can calculate the voltage in the primary coil from Faraday's law. So we can say Vp is equal to MP times by the change in flux over the change in time. And we can have a similar equation for the voltage induced in the secondary coil from Faraday's law. So we can combine these equations together. We can say Ns over MP is equal to Vs over Vp. So let's summarize what we've learned in today's lesson. The transformer equation is Ns over MP is equal to Vs over Vp. The transformer efficiency can be calculated by the equation Is times by Vs over Ip times by Vp. We should be able to understand about the production of eddy currents and understand the causes of inefficiencies in a transformer. And we should also be able to understand the transmission of electrical power at high voltage, including calculations of power loss in transmission cables. So if we've been successful and learnt in today's lesson, we should be able to describe what a transformer is and explain how it operates. We should be able to calculate values of a transformer system, and finally explain how a transformer works, including its inefficiencies. So I hope you've enjoyed today's lesson on the operation of a transformer, which is part of the magnetic fields topic in AQA A-Level Physics. Thank you very much for listening, and have a lovely day.